In this problem, knowing that the allowable normal stress for the steel used is 160 megapascal, select the most economical S-shaped beam to support the loading shock. So as we discussed, sometimes we have standard beams used. So after getting, if you want the value of S minimum from design, we go to the appendix and select several available possibilities, and then the appropriate choice will be the one with the smallest cost, which correspond to the smallest weight per unit length. So first, as usual, we start by drawing the shear and bending moment diagram. As usual, we find the external reactions, then we draw the shear and bending moment diagrams using or area method or section method. Here, you can predict that the bending moment will start by 0 at A and will end by 0 at C. Concerning the shear, it will start by AY and it will end by a value equal to plus 80, because the 80 kilonewton downward force will bring it back to 0. So this is an overall what is expected. Here you can see the shear diagram and also the bending moment diagram. So we start at A by 0 and we end up at C by 0 for the bending moment. Now, please try to practice with these diagrams to make sure you are able to get the actual values. Now we'll move to the design part. Once we get the shear and bending moment diagrams, as we discussed here, since we are dealing with a nest shape, so we have C1 equals to C2, so we just consider the absolute value of the bending maximum moment, which is here 256. So we can now find the value of S minimum, since we have the bending maximum moment and the allowable stress. We get that S minimum should be 1.6 times 10 to the power minus 3 meter cube, which is equal to 1,600 times 10 to the power 3 millimeter cube. And now I should go to Appendix C to select possibilities of standard beams for which S is larger than 1,600 times 10 to the power 3 millimeter. Let us go to the appendix. If you look at your appendix, this is the first you go for S shapes, okay? And you check in your table here, you want Sx to be larger than 1,600. And you can find several possibilities. Of course, you will select the one with the smallest cost. So already, all of these are already possible because S is larger than 1,600. You can go down to this level. Here you should stop, okay? So these are all possible cases, because if I continue below this value, I have then values smaller than of S smaller than 1,600. So my first choice, okay, I can select 1,690. Why I don't say directly this is the actual value? Because as we said, we should try to select the one with the minimal cost. And the minimal cost correspond to the minimal weight per unit length. If you remember when we talked about the way we name the beams, so S will the letter is for the shape, this is for the nominal depth in millimeter, and this is for the weight per or the mass per unit length. Okay, and you can check this always here. They will tell you that how to name your beams. So according to American Standard Beam, we have letter S is for the shape, followed by the nominal depth in millimeters and the mass in kilograms per meter. So now, after you say the first criteria is to get S larger than 1,690, I should select between these the one with the smallest mass per unit length. So you should check now this number, because this number represents the mass per unit length. As you can see, 184 is larger than 98.2. And 98.2 is the smallest uh, number between all of among all of these numbers. Okay, so I should select then this value, because this is acceptable since s is larger than 1600, but it is the best because it represents the smaller cost, since the mass per unit length is 98.2, which is the smallest possible value among the available choices. Okay, so you can just say that these are the two best choices, but between them I would select this one because the cost is the most important factor for me. After I ensured the safety. The safety is ensured by a value of s larger than 1600, and then I can select the most economical type, which is S510 and times 98. So this is the beam I will select. So please pay attention in the selection. Uh, I don't have to be as close as possible to 1600. I just have to ensure that it's larger than 1600. The most important criterion then will be that the weight per unit length is the smallest, or the mass per unit length is as small as possible. Okay, of course, after satisfying this condition. So because these two satisfy the condition, I don't select the one with closest as to 1600. No, the most important criterion is then the mass per unit kilogram. This is the lightest, so it's represents the smallest cost. So on the economical level, this is my best choice because it's satisfying the condition of a non-failure, and at the same time it's the most economic. Let us continue with design problems. And in this problem, this is a very important problem where we have different cases to consider. And this is what we were talking about when we have C1 different than C2. Until now, in all problems, we're considering symmetric cross sections. C1 equals to C2, it's equal to C. However, here you have a non-symmetrical cross section. So you have a value for C1, a value for C2, plus also they gave you different allowable stresses for tension and compression. So this will affect the choice of your permissible maximum bending moment. Okay, so we have in this problem beams AB, BC, and CD have the cross section shown and are pin connected at B and C. As we discussed together, whenever you have pin connected beams, so you have hinge at B and a hinge at C, bending moment at B should be 0 and bending moment at C should be 0, because we can consider that we have three parts connected together, AB, BC, and CD. And we know that at an extremity where we don't have a couple, or we don't have a reaction as fixity, then we have the bending moment equal to 0. So knowing that the allowable normal stress is 110 megapascal in tension and minus 150 megapascal in compression, determine the largest permissible value of P in B if B in BC is not to be overstressed. Okay, so here I should pay attention a lot in my design. I should consider all critical cases and select, if you want, the most critical value between the different critical cases. So I have first, I should not reach a tension larger than 110 megapascal. I should not reach a compression stress larger than 150 megapascal. and I should check for the calculation for the maximum of, if you want, positive moment and the maximum negative moment here, because I have C1 and C2 are different from each other. Okay, so the first step to do is to draw the shear and bending moment diagram. And since P is unknown, I will express values of shear and value of bending moment function of P to determine my critical bending moments. Okay, and then this will allow me to determine, if you want, what is the maximum value of P to not exceed uh, the allowable stress in tension and in compression. To start with, let us do a small analysis of this beam. Look, if you take a look, you can see a symmetry. You have a symmetry for in the load and the symmetry in the beam. So you can directly say, because of symmetry, AY is equal to DY is equal to P. So you can determine the reaction at A and D, and these reactions are equal to P because of symmetry. Okay, and this will help you then into drawing the shear diagram and the bending moment diagram. Now, to start with, as we discussed, we have a value of reaction at A equal to P, and at D also. So this is why, if you want to draw the shear diagram, we'll start by a positive jump at A, because it's a upward reaction equal to P. Now, as we discussed before, any internal pin or hinge will not cause any jump in shear or any variation in shear, because by action reaction, as we said, the effects will cancel out, and then when you go from A to this point, you don't notice the presence of the hinge. So the shear will be constant from A to this point here. Okay, so if we call this point E, for example, and this is F, so from A to E, shear is equal to P. And at E, you have a downward concentrated force equal to P, so you will go down to 0. Between E and F, no shear. Shear is 0. Now, at F, you have a concentrated force of minus, it's negative. It's a downward force, so you have a negative jump. So you will reach minus P, and you will maintain this value until D. And as expected, the upward reaction at D will bring just your shear after D to 0. Okay. Also a note: whenever you have symmetrical beams with symmetrical supports and symmetrical load, the shear will be anti-symmetrical. Okay. While the bending moment will be symmetrical, and you can observe this from your diagram. Okay, why you have this? Because look, whenever you take left and right parts, you can see that the convention of V. So if you put like here a mirror, you have anti-symmetry about it for V. However, for the bending moment, you have symmetry. This is why you will get symmetrical behavior in bending moment. So you can just plot the bending moment until the middle and deduce the other part by symmetry. While for the shear, you will have, if you want, symmetry with respect to point, not with respect to an axis. It's anti-symmetry with respect to the axis. And you have symmetry with respect to the point. So if you draw the shear and bending moment diagrams, you can verify this. So for V, you have symmetry about point O. Okay. And for bending moment, you can deduce your bending moment diagram from your shear diagram. First, since you have a fixity at both extremities, you will expect that the bending moment will not start by 0. And to get what is the value of the bending moment at A, all you have to do is to do a section, or to so if you consider this part, okay, part AB alone. So if you take part AB alone, you already know that P is up here because AY is equal to P, okay? And because of AB is, when you treat part AB, this is an equilibrium and you don't have a bending moment at B. M at B is 0. So you can use that the bending moment at B is 0 to get what is your reaction, what is your moment reaction at the fixity. To get the moment reaction at the fixity, you know that for this part of the beam, sum of forces equals to 0. So at B, the reaction is, or the shear, if you want, is downward. So you have a value of shear equal to P. And then to get the moment at the fixity, you say that sum of moments about A equals to 0. So this is A. Sum of moments about A equals to 0. If I consider the counterclockwise as positive, I have plus MA minus P times this distance. This distance is A. So minus P times A equals to 0. So the reaction moment at the fixity MA is equal to P times A. Okay, and now between, if you want, between B and C, if you want to draw the bending moment diagram variation, it's very simple. You can use now the shear diagram because you have already the initial value of bending moment at A. The initial bending value, as we discussed, is because the fixity moment is, look, this is your fixity, and you have a counterclockwise moment at the fixity. We know that when we move from left to right, and when we move from A to D and we want to draw M function of X, a counterclockwise moment will cause a downward jump. This is why you start at A by a negative value of bending moment, which is minus P times A. Okay, now if you go to your, if you want to plot M, all you have to do is to say that from A to E, as expected, I should have a bending moment at B0 because it's a hinge. And as I go from A to E, the increase in moment is equal to the area under this curve. We know that the distance from A to B is A, and the distance from B to E is 2.4. So this part is A. So you have until here, as expected, the area is plus P times A. So we'll go to 0 at B, and from B to E, this distance is 2.4. So the increase of moment from B to E is P times 2.4. So you can say that the bending moment at E is equal to 2.4 P. And now from E to F, nothing will change because we don't have anything. Okay, so you just have, it's pure bending. If you remember the chapter of pure bending, between E and F, shear is 0, and you just have a constant bending moment. This is a pure bending application. So from E to F, it's 2.4 P. And now no need to continue because, as we discussed, bending moment is symmetrical with respect to the vertical axis of the beam. So here I can just consider that for the remaining part, I can exactly have the symmetry. So at this point, I have minus P times A, and that's it. Okay. Now, what can I deduce from my bending moment diagram? From my bending moment diagram, I have a maximum positive moment of 2.4 P and a maximum negative moment of P times A. and I want to design the system to not exceed the allowable stress. Okay. Now, let us to be able to do the analysis of what is the maximum load P to be applied. Let us determine first what is C1, what is C2, and in case of maximum positive moment, what is my corresponding value of bending of stresses applied, okay, and the corresponding value that P should have to not exceed this value of sigma. Okay, so first let us go back to our figure. As we discussed, top and bottom are not equidistant from mutual axis because we don't have a symmetrical cross section. Whenever you don't have a symmetrical cross section, the procedure will be to determine the location of the neutral axis. So if we go back to previous chapter, we know how to detect the position of the neutral axis. It should pass by the centroid of the cross section. So we do a table to determine the position of the centroid, and we consider that the centroid is determined as y centroid equals to summation of ai yi over ai. So here we can divide our cross section into two parts. This is part 1, and this is part 2. Okay, and we can take as origin as reference this level, and this is y. So we have y1, y2, a1, a2. They are very simple to calculate. You have rectangles here. So let's say for a1, it's 12.5 times 150 millimeter, and y1 is at 75 over 2, 150 over 2, which is 75 millimeter from the bottom level. And for the upper part, the area is 200 times 12.5, and the value of y2 is 150 plus 12.5 over 2. Okay, so now we can determine the position of the neutral axis by getting y bar. And of course, don't forget to get the total inertia of your section about the neutral axis. You should apply the parallel axis theorem because for each rectangle, you know the inertia about an axis passing by its centroid. And then because you want to convert back to the inertia about neutral axis, then you should find the distance between. So this is the neutral axis level was found at y bar equal 121.43. So now you can consider what is y top and y bottom. So C1 is equal to the total height that we have minus the position of centroid. Okay, the total height, if you go back to the figure, is 150 plus 25, or sorry, plus 12.5, I think. Let us go back to the figure. So the total height is 150 plus 12.5. You subtract from it y bar of neutral axis, you get C1. And to find C2, C2 is simply the y bar, because C2 represents the distance from neutral axis to the bottom. So C2 is equal to y bar, which is 121.43, while C1, which is the top y, C1 is equal to 162.5, which is the total height, minus 121.43. So you can get this is equal to 41.07. Okay, so now you have the value of C1, C2. So, and you can calculate now the total inertia of your section. The total inertia, of course, about the neutral axis. To do it, you already you divided your section into two parts. For rectangle 1, you know the inertia about the axis passing by its centroid, and then you can determine what is the distance between this axis and the neutral axis. So to do it, you just have to subtract from 41.07 this distance, which is 12.5 over 2. Okay, so the distance from between the axis passing by the neutral axis and the axis passing by the centroid is 41.07 minus 12.5 over 2. And by applying the parallel axis theorem, you get the inertia of this part, which is bh cube over 12 plus ad d1 square. Now you do the same for the second rectangle, and you add both inertias to get the total inertia of your section. And now you can calculate the value of I over y for the top and for the bottom. Okay, both are of interest here because you have C1 different than C2, and you can do the calculation based on the most critical one. How to know which one is the most critical? Our purpose is to find what is the maximum allowable value of P to not exceed the stresses. Okay, now we know well that the bending moment limits are found by relating the bending moment to the allowable stress. We know that the maximum possible bending moment to be calculated is related to sigma times I over y. Okay, so now you have two values of I over y, one for the top, one for the bottom. And also you have two values of sigma, one for compression and one for tension. And then if you do a small analysis, if you want, no need to calculate the four possible values, the four critical values of M. You can directly say, since I am interested into a limit, I want to find the limit of bending moment, and I have four critical values. What are the critical values? Okay, first, you have if you have a positive bending moment, okay, a positive bending moment will cause a compression of the upper part and the tension of the lower part. So if you go back to your figure, going back to your figure, you have that this is my top, this is my bottom, okay, and points E and F, points C and F here correspond to maximum positive moment. So this is maximum positive. And you have also a maximum negative moment, which is an absolute value equal to P times A. Okay. Now, to start with, okay, if I have a positive moment, okay, at which is at E, taking place at E and F, a positive moment will cause a compression of the upper part and tension of the lower part. Okay, so, and we know that for compression I use C1 here, for the top I use C1, for the bottom I use CP. Okay, so now when you take the case of maximum positive moment at E and F, you can get that the values of maximum compression and maximum tension. So corresponding, whenever I have the maximum bending moment, I will have the corresponding tension at E and F that is allowable, okay, is, you know that in tension limit is 110, okay, and the whenever I'm dealing with a positive bending moment, then the lower part will be in tension. So I will take here at bottom, what is the value of I over 1, okay? Because as you can see here, I have two values, top and bottom. Of course, you can say, since I'm designing to find the critical value of moment, I should take the minimum between the different critical cases. You remember when we have a maximum bending moment to not reach compression allowable value, or maximum bending moment to not reach tension allowable value. When I do the calculation, I select the smallest at the end. Okay. Here, this is what we will do. We'll do calculation for the four critical cases and select the minimum. If I do a small analysis, I can know which one will be the minimum. But let us now first do typical study, find all critical values, and then select the minimum between these values. So how to think? We say that when the maximum, when I have a positive bending moment, the upper part will be compressed, the lower part will be in tension. Okay, so whenever I have, if I'm doing the analysis at points E and F where the bending moment is positive, then I can say that top is in compression, bottom is in tension. So I will take the allowable limit of compression, which is 110. So as you can see, sorry, for tension you have 110 allowable stress. For compression you have minus 50. Since you are considering the case of a positive moment, then you have the upper part in compression, so you will use with the allowable compression stress, which is 150, you will use I over Y of top. Okay, and with the limit of tension, you will use I over Y of bottom. This will give you two maximum values that the bending moment should not exceed. So if you go back to your calculation, you say that whenever I'm considering maximum bending moment with the value of tension, the allowable stress to not exceed is 110 times 10 to the power 6, and tension is taking place at the bottom. So I consider I over Y at bottom level, and in this table, I already calculated I over Y at bottom and I over Y at top. Okay, so you can see here, that I get a first critical moment. This is not to exceed the maximum allowable tension. So this is if you want M max to not exceed at points E and F, okay, to not exceed the maximum tension. And I have another value to not exceed the maximum compression, which is equal to sigma compression times I over Y at top. Okay. Of course, here, for example, you can directly know which one is more critical. Why? Because look, the bending moment limit is equal to the product of sigma times I over Y. Okay. So in this case, the critical moment will of course be tension at the end Fy, because tension has the lowest allowable stress, and also, okay, it's occurring at if you want for I over Y that is smaller, the smallest between the two, because C2, if you go back to the figure, Y represents C here. Okay, so tension is for C2 and compression is for C1. So you have that first sigma tension in this problem is smaller than sigma compression. Plus you have that for a positive bending moment, okay, tension is taking place at the farthest distance from the neutral axis. So since C2 is also larger than C1, C2, which corresponds to the side of tension, is larger than C1. And sigma allowable tension is smaller than sigma allowable compression, you can be sure that the most critical case is for tension. Because as you can see, you know that you should select the minimum between these two. Okay? You should select the minimum between these two. And M is the product of sigma times I over 1. I is for the whole section. It's the same in calculation of tension and compression. But Y, for tension, you will take I over Y bottom, so you'll take C2. And for compression, you will take C1. So since M is inversely proportional to C, larger C2 will lead to smaller M. And smaller allowable stress will lead to smaller M. So here you can be sure that the critical value of bending moment will be for tension at T and F. Okay. You can verify this by doing all possible scenarios, all possible critical cases. So the first case is when M is when I take a positive bending moment at E and F. And I consider the case of not exceeding the tension and the compression state. Now, if I go back to my free body diagram, at A and D, I have a negative bending moment. So at points A and D, the situation will be reversed. I have the bending moment now that is in the opposite direction. So it's causing compression of the bottom part and tension of the upper part. So now if I want to calculate the limit of M to not exceed the maximum tension at A and D, okay, for tension, I will use the allowable stress of tension and I will use I over Y of the top, which is correlated to C1. And for compression, I will use sigma of compression times I over Y of bottom, which is related to C2. And as you can verify, the most critical bending moment is the smallest one, because you have that the bending moment should be smaller than 9.622 and smaller than 38.8 and smaller than minus 28. And an absolute value, it should be smaller than 28.45 and smaller than 13.121. So when we talk about a critical value, okay, the most critical value will be the one that is smallest in absolute value, which is 9.622 times 10 to the power 3. Okay, so here if you want, you have two constraints here. One, when your maximum for your maximum moment positive, and one for your maximum moment negative. If you consider for the analysis of this is for the analysis of M max positive. For M max positive, M max positive should be smaller than 9.622 and smaller than 38.8. Which one is more critical between these two? This one is more critical. Okay, so you can be sure that your maximum positive bending moment should be smaller than 9.622. Okay, and now since you expressed your maximum positive bending moment function of P, because if you go back to your analysis and shear and bending moment diagram, you can see that the maximum positive moment is equal to 2.4 P. And 2.4 P should be smaller than 9 point, the value we found. So when we did the analysis of maximum positive moment, we found two values for this maximum. We select the smallest, okay, which correspond here to 9 point something. So now you can find what is the minimal value of P to satisfy the first condition, that you are not exceeding the allowable stress of tension and compression for a positive bending moment. Now for the negative bending moment, you have minus P times A. So already now P is imposed. Now you can design for A. You have that P times A should be smaller than, now you will select the most critical between the two cases here, which are when I have a negative moment, we said that we have tension at A and D and compression. Tension at A and D will take place at the upper level. So you take here the first critical value of the bending moment is sigma tension times I over Y at the top level, because for a negative bending moment, as we discussed, the upper part will be in tension. So to get the corresponding maximum moment in the negative case, I should multiply the tension stress or tensile stress by I over Y at the top level, which is 258.6 times 10 minus 6, while for the compression, I should take the allowable stress times the value of I over Y at the bottom, which is minus 87.47 times 10 minus 6. Here, you should do calculation. You cannot predict which one will be more critical. Here, you could predict it because you have a larger value of smaller value of allowable tension compared to compression, and also here I over Y is smaller because you are having larger C. So you can be sure that this is more critical. Here you should perform calculation. You cannot know because already 110 is smaller than 150, but 258.6 is larger than 87.47. So to know which one is more critical, you should do both calculation and then select the minimum. The minimum is this one. Okay, so just for the case of positive bending moment, you can expect that the most critical is tension at E and F because it's characterized by the smallest allowable stress and the largest distance, which is C2 from the neutral axis. However, in case of negative bending moment, you should do both calculation. You should do tension at A and D and compression at A and D to make sure which one is more critical. Here, it's clear that the most critical one is the one with the smallest absolute value, which is 13.121 times 10 3. And you know that the bending moment, whenever you are at A or D section, is minus A times P, is minus A times P. So all you have to do then is to multiply, is to say that minus A times P should be is equal to, as the critical case, to 13.121 times 10 to the power 3. And the value of P is already calculated from previous step. So you can deduce what should be the value